Okay, hello, and welcome to the asset build system of Far Cry 5. May I please remind you that to turn off your phone and please fill up the survey at the end of the talk, please. So my name is Rémi Quenin. I'm the engine architect on the Far Cry franchise at Ubisoft Montreal, and we're here today to talk about pipeline. I'm glad to see you there today because I find out that usually asset talks and pipeline talks don't get as much love as they deserve at conferences. And still, it's a really important subject. I've seen in many small projects, asset build left to a poor intern working with buggy scripts on an old workstation transformed as a build machine. And every time this mistake has been done, when the project gets bigger, the asset build system becomes the bottleneck of those projects. And for a project of the size of Far Cry 5, this is clearly not an option. We wanted the exact opposite state-of-the-art build system. Because Far Cry 5 was indeed quite a big project. The project counted about 1,000 people that worked on the project at peak across 5 studios and lasted over 3 years, started right after FC4. And it features a gigantic open world which is twice the size of what was Far Cry 4 and Far Cry Primal, with 80 square kilometers of playable area. So such a big world and such a huge amount of people are generating a lot of data. One nightly build was about 560 gigabytes of outputs every night. And this is for the main world on the 3 platforms we're shipping on, which is Xbox, PS4, and PC, but also for a few test maps that the production needs on a daily basis. And in order to produce these outputs, the build system was performing over 4.5 terabytes of I/O to produce this build. This accounts for the 3 platforms. This resulted in a dependency graph that counts more than 20 million nodes, which is quite big. So all this data is saved on Perforce. Most of our source data is saved on Perforce by our artists in an intermediate format. And usually when we run the engine, those assets are converted to a binary format that can be loaded by the game as saved in a temporary folder on the target machine. So today we're going to talk about this transformation, going from this source data to the binary data, and we're going to focus actually on the process of binarizing the assets. First, I'll be talking about the architecture of a pipeline on Far Cry to properly understand what is the place of the asset build system in there. Then we'll be able to talk actually about the asset build system and how it works. I'll get through a few of its features that helps making the build even faster. But first, let's talk about the pipeline itself. And let's talk about where we were at the end on Far Cry 4. One of the biggest problems we had at the end of Far Cry 4 was the fact that a lot of our tool code was still in C++. That means a lot of our tools and engine code links together, and it ends up with the strong runtime and tools coupling, which is a big issue because you have some tool code that can stick into the final engine that we will ship. And you also produce one big monolithic editor that is that all the tools are in the same executable. So whenever you want to use one of those tools, you need to load all of them, which is quite a problem. And so we have long load time just to use one tool. So on Far Cry 5, we wanted the exact opposite. We wanted to have some modular specialized tools that have few dependencies that can load fast, and that have a clean data separation between the tools themselves and the runtime itself. That means we want the tool to have a set of data. This data needs to be converted into a binary format for the runtime. The runtime only knows how to read this optimized data and not the tool's data. And also wanted those tools to have no direct dependency on the engine, so you can focus when you work on a tool on the user experience and not on the problem that you may have with the interaction with the engine. So how can we achieve that? So our solution is called what we call the engine as a service. And to properly understand what is the engine as service, we have to look at where we got our inspiration. And if we look at the giant technology companies out there, such as Google and Facebook, we can see that those guys have several projects, but all those projects are running on server side. And they're actually providing all their features through a set of high-level APIs that are then consumed by the front end that just focus on the UI. So we have a very clear separation between the back end that implements the feature, expose those features through a set of high-level APIs, and the front end that consumes those features through a transport layer. In that case, it's HTTP. So if we look at this architecture, we can actually apply the same concepts for tools and our engine. Our engine can actually be seen as a backend. It has a lot of features. It has a render particle system, some game plan AI systems. And all of those systems can expose their features through a set of high-level APIs that can be then consumed through a transport layer, in that case RPC, by a front end, and the front end in that case would be the tools. Such an architecture have a lot of benefits. The first obvious one is that we have a clear separation of concerns. On the engine side, we do engine stuff, and on the tool side, we just focus on tool stuff. And it also forces you to use the right technology. So you can use a native language for the engine and a high-level language for the tools themselves. It also allows to build the tools in an environment that is really light, so you can have fast iteration, and we all know that iteration is key for quality. We have one big difference, though, compared to the web services software. We need to feed back the data that we're producing to the engine. As I said before, we only want the engine to consume binarized data. So this data needs to be converted on the fly, and this is where the build system comes into play. We need an asset build system that will do the conversion from the source data to the binarized data. Having a third component like that allows you also to do some JIT compilation just in time. So whenever the engine requires an asset, it can ask the build system to build these assets. This asset then will be ready just in time whenever required by the engine. So let's go through a really small example just to properly understand how those three components work together. Imagine you want to write a tool such as this one to just show a particle. You want to spawn a particle and have a preview of this particle. So what you expect by executing this code is actually have a viewport and see your particle in a viewport. So what will happen when you do that? First, you're going to load your tool executable and start executing the code. So creating an engine. Creating an engine will spawn actually an engine process. And this engine process will spawn for itself an asset build system, so you can delegate all the asset builds to this asset build system. Then we start executing one line of code like this one. So making the call through the set of high-level APIs. We're making the call on the tool side that will be executed on the engine side. And we have some kind of similar code that will be executed on the engine side through the API. And then we're going to spawn our particle. By doing so, we'll discover a lot of resource or asset references while spawning a particle, some textures, some sound, some whatever. And so some communication will happen between the engine and the asset build system to have all those assets ready to be used and binarized in a proper format. So this is just a really simple example to properly understand how those three components work together. So what we've seen here could be a tool for an asset preview, but using the engine as service can be used in many other situations, such as an asset editor, to build some augmented debugging tools, to build some automated testing, tech prototyping, and more. So this is really the tip of the iceberg that I'm talking about here, about the engine as service. So what we need to keep out of that is that the runtime of the engine is used as a service. So there is no tool code shipped with our engine. Then we can build some independent modular tool on top of that. But when you do that, you need a third component, which is the asset build system, that acts as a junction between the two first components. So let's get into the details of how work the asset build system. So first question we need to answer, it was actually what do we expect out of a build system? what do we expect out of it? So what we want to turn a source asset into an optimized asset, so in binary format with all the tool information stripped out, in order to have the fastest loads as possible in the game, and have the data built in a way that is platform specific, the best possible format for the target platform. So imagine we want to build an asset which is a particle asset, and this particle asset is a file that contains some parameters in a binary format, plus some vertices. Building this asset, we need to open some files to find the source data. So we have some kind of dependency over a parameter file. We'll have also some dependency over some vertices that will package into the final assets. But we can imagine that those vertices are actually already built in a form that is platform specific, optimized for a target platform. So those vertices have themselves another dependency over the platform agnostic geometry. So what we can see here with this really simple example, that we are building a graph of assets that have dependency with each other. So we can actually define a build as being a set of independent build actions that have dependencies and can produce outputs. And all those build actions together form a graph, a dependency graph, where every dependency needs to be satisfied in order to process the node. The very first thing I'd like to stress here is that the dependencies are actually defining the speeds of our build. And let's go through a simple example to understand what I mean by that. Imagine we want to build an asset A. To do so, we first need to list all the dependencies of this asset. Here, let's say it would be asset B and C. Then we have to build those dependencies. Once it's built, we can actually build our asset. And when this asset is built, we can notify all the dependent assets that our asset is done, and it can be used. So imagine now we can run this graph on a machine that have several cores. We can actually build asset B and C at the same time in the first step, and then in the second step, build asset A. Imagine we have the similar graph with other assets, D, E, and F here. Everything can happen at the same time. So in 2 steps, we can actually build all of those 6 assets. Now imagine we had just a simple dependency between asset A and E. Suddenly, it takes 4 steps to have all those 6 assets built at the same time. And the same goes for incrementality. Imagine here, just asset B has changed. If it has changed, you need to rebuild asset B and asset A. So in 2 builds, you can have all those 6 assets up to date and ready to be used. But with the additional dependency, you now need 4 builds and 4 steps to have everything up to date and built. So here, what we see is just a simple one single dependency can make your build twice as long or twice as fast, depending on which way you're looking at it. So it's what I mean by the dependency actually defining the speed of our build. And define the speed of our build for 2 main reasons, and it's probably the most important slide of this talk. Because it defines the parallelization opportunities, and it also defines how incremental a build can be. It's just what we saw. So it's all about dependencies. So dependencies, dependencies, dependencies. So talking about dependencies, we can actually categorize dependency in 2 big families. What we can call the compile dependencies, the dependency that needs to be satisfied in order to build an asset that have an effect on the outputs. And we can oppose them to the runtime dependency, which are just simple reference required to run. But let's look at this first family of dependencies, the compile dependencies. So all the dependencies that have an effect on the output. They can be also split into 2 categories, what we can call the static dependencies and opposed to the dynamic dependencies. The static ones are the ones that you can list up front. You know right away that you need to open this source file to produce these outputs, whereas the dynamic dependencies are the ones that you need to discover. You need to open your static dependencies, discover that you have a reference to some other files, and then this will be a dynamic dependency. You don't know it right at the beginning. You need to actually analyze the static dependency to discover these additional dependencies. Just properly understand that, imagine that we want to build an object file. We all know that as a programmer. The static dependency on object file in C++ would be the CPP file. We know right away that we need to compile the CPP file to produce this object file. But once we open this CPP file, we may discover that we have some includes in this CPP file that also have an effect on the outputs. Whenever one of those header files change, we need to rebuild the object file actually. So it is a compile dependency, it has an effect on the output, but it's dynamic because you need to open the static dependency to discover it. The same would go for the particle when talking about just before. The static dependency will be the definition file itself, but once you open this file, you may discover a reference to the geometry that you want to package in your final particle assets. So you would have, as a dynamic dependency, this geometry, this vertex buffer. The same would go for a texture, for instance. Texture, the static dependency will be the PNG file itself, but once you open this file, you may discover that a certain texture profile is associated to this texture that said that it's a diffuse texture, a normal map, or whatever, and it changed the pixel format of the texture. So this would be a dynamic dependency. An animation, static dependency would be the animation source file. So it may have a dependency over a skeleton that describe actually what are the bones you're trying to animate with this definition file. So we can oppose to the compile dependencies the runtime dependencies. The runtime dependency has no effect on the output. It's just a simple reference to another asset. But they will be required to run actually. And actually, those ones can be emitted while you're building your asset. You will discover that you have a reference to another asset while building your assets. So you emit these runtime dependencies, and this other asset will be actually used at runtime whenever you want to use your asset. So for instance, a material may have some runtime dependencies over a texture. Your material file itself won't be affected by the texture itself, but when you want to use your material at runtime, you need those textures to be here and ready to be used. The same would go for a geometry that may have some dependencies over a material. So the material doesn't affect the geometry itself, but will be required whenever you want to display this geometry in your engine. The dialogue may have some dependency over sounds or facial animation, won't change the dialogue itself. Animation may emit some particle or play some sounds when you're actually playing this animation. And some particles may have some dependency over textures and sound that needs to be played when you're actually spawning your particle. So in Far Cry 5, our asset build system is called the PPD, which stands for Prepare Platform Data. And it actually implements all the things I just described, the dependency graph, with the static and dynamic compile dependencies and the runtime dependencies. And everything in our system is a node. So that means an asset is a node within the graph. A source file is another node within a graph. And if two assets actually depend on the same source file, those two assets will have a dependency over the same node, the node that represents this file. And every node in the graph will be just evaluated once. A nice consequence of that is that for every file, we're just going to perform a single I/O per file because it's just one node, and each node is just evaluated once. Another strength of our system might be its modularity. By that I mean, so we have the graph with all the nodes, but each node is actually associated to a processor. And the processor is the part that our user need to write in order to write some code for an asset build system. The processor is just a collection of callbacks. One of them is for sure the compilation itself, the compilation function, but it's also a callback to actually gather the dependencies of a given asset. The framework then perform all the call the callbacks at a proper time and perform all the graph evaluation work without the user having to write anything about that. The only thing the user needs to write is actually the processor. The processor is just the two callbacks, build and gather dependency. A nice effect of that, of this modularity and not having to write a lot of stuff within the system, is that it provides a kind of easiness of implementation. Our users just have to write these two simple functions. And what we saw on this project, we have many people that we were afraid before to write some code for the pipeline because it was too complex. And in this project, we had some people that already jumped in and started writing some code for the asset build system. So we can actually remove some code that were usually executed during runtime. So to perform some task offline. So it's a net win for the game. So it was a nice consequence of the modularity. Another strength of the system is what we can call the reverse API. What I mean by that is whenever you want to build an asset, the only thing you need to do is ask build this asset. What I mean by that, imagine you use a compiler. Usually what you do, you invoke your compiler, you say, okay, compile this source file into this destination file using this settings file. So you actually need to know a lot about the thing you want to build because you need to provide a lot of information to the compiler. Here, you don't need to know any of that. You don't need to know the asset at all. Actually, you just say, build me this asset. Then the framework knows which processor the asset is bound to and can call the proper callback on the processor. So it can gather the dependencies by itself. It can then build the asset by itself. And so you don't need to know anything about your asset. You just say, okay, build this asset, and the framework take care of everything else. So then it will unroll the dependencies, making all the call to the callbacks of the processor, gather all those dependencies recursively, and your build will be as long as you have dependencies, because remember, this is the dependency that defines the speed of your build. So let's go through a real-life example to see actually how it will enroll building an asset within our system. So the particle we're talking about, so imagine that it's the asset is an output file we can call particle.bin that consists of some parameters and vertex buffer. The static dependency will be the definition file, and the dynamic dependency will be the trim geometry, as we said before. And we may have some runtime dependency that would be textures and sounds. So what the user asks would be just build me this asset. Then the framework will go through the first phase, injecting the static dependencies. So making the callback, gather the dependency will be the definition file, and then wait for this definition file to be ready to be used. It's just a simple file on disk, can be used right away, so it can be considered as build. So then we can move to the next stage, which is injecting the dynamic dependencies. So we would inject the trim geometry as a dependency. This one itself will inject its own dependency, will be the fat geometry, and wait for it. It's just a simple file on disk, so it can be considered built right away. Then our trim geometry can start building and save itself on disk. Then it can be used by the particle itself. So we move to the third stage here and build the particle itself. And while building, we could emit some runtime dependencies that would be those textures and sounds. Another example I'd like to talk about is what we call settings, because all engine out there are actually featuring such type of assets. Settings can be seen as just a set of parameters that are usually edited through a property grid. And usually those are the fields of C++ class or structure exposed through C++ reflection. So our engine is actually implementing C++ reflection, like almost all engine out there. So I'm not going to talk about that. There is a lot of content online about the subject. But one thing we need to note about that is that thanks to C++ reflection, we can actually automate serialization. So imagine we have this structure that has two parameters, an int and a float. The idea here is using the reflection system is to generate a file that describes this structure. Then this file can be actually used by your tools to edit those settings. So the tool can load this file, and you can then edit those settings through the property grid and save those results into different files for each instance that we want to make. Whenever we want to use those instances inside the engine, we can then go through the asset build system, binarize those settings, and then it can be used by the engine. So if we look at that through the perspective of the asset build system, the asset here is this binary file. And this binary file has a static dependency, which would be the instance file that contains the settings. When we open this file, we actually see that those settings are settings for a given type. So we can actually depend dynamically over the definition file of this type. But we have to see here also that this definition file will depend on the code itself, on the executable, because whenever you change the code, you add some parameters, you remove some parameters, this definition file might be affected, needs to be rebuilt, so we have this dependency over the executable here. This also shows that we may have some, whenever we change some code, sometime we need to actually rebuild some assets. It is particularly true when you change actually the compile function. Let's say you want to change your texture compiler to change the compression format. You need to rebuild the texture. So we achieve that through versioning. The idea is quite simple. We have each processor has an hard-coded version number within the code. And whenever we build something, we save this version number within the asset. So whenever we load the state of the build, we can see that the version may have changed. And if it has changed, we need to discard all the nodes that were associated to the previous version of the processor. And we need to recursively go through all the dependencies of those assets and discard recursively all those nodes that were depending on the node that has been discarded. So the more dependency you have, the more things you're going to discard because the dependencies are actually defining the speed of our build. One last strength I'd like to talk about our system is the multi-threading. Here, every stage is a task. What I mean by that is the static dependency injection is a task. The dynamic dependency injection is a task. The build itself is a task. They're all separate tasks that can be parallelized. And everything is notification driven. So you spawn a task for your dependency, you register a notification. And when you receive the last notification of your dependencies, you know that you can move to the next stage. So for instance, if we ask our build system to build a particle, first, the only thing we need to do is actually schedule the first stage, which is inject the static dependency. Static dependency will actually schedule itself. The dependent asset will be the simple file and register for notification. Whenever it gets its notification, it can move to the next stage, which is injecting the dynamic dependency. Scheduling a dependency itself is just scheduling the first stage. We would schedule the trim geometry static dependency injection. This one itself will schedule the fat geometry file check. Whenever we see that this file is up to date, we receive the notification, can move to the next step, building the trim geometry, then notify, then build the particle. So what we see here, just building a simple particle is going to generate a lot of tasks, and this is just for one geometry, one particle. So we are building thousands of assets at the same time, so we have actually a huge amount of tasks to execute at the same time. And this scales extremely well on PCs that have a lot of cores. So in case or in Far Cry 5, we're using a 48 cores machine, and we can actually get this machine quite busy doing this work. One big consequence of doing that is we have a blazing fast no operation. And the no operation is basically you have built something and you just ask right after to build it again. So there is actually nothing to build. Everything should be up to date, but you still need to check all the references on disk just to make sure nothing has changed. So a no-op build is actually a way to measure the overhead of your system and how your graph parsing logic is performing. So in our case, as we just saw, the graph logic itself is completely multi-threaded because everything is a task in our graph. So the entire logic is completely multi-threaded and is also written in highly optimized C++. Many build systems out there are actually making call to external executable or calling scripts or making that kind of stuff, and which make the build actually long to just evaluate the graph. In our case, everything is written in a highly optimized C++ in just one executable. And on top of that, we actually carefully crafted all our data structure and to be as cache-friendly as possible, trying to minimize as much as we could the amount of allocation we're doing. So just to have as fast as we can the graph logic parsing. The result of that is we're just hammering completely the file system when we're doing a no-op build, and the limiting factor becomes the local disk, and we become actually IOPS bound on the local disk, which is quite a nice place to be. So if we need to keep three things off of this part, would say that our build system is implementing a dependency graph, which is represented by the compiled dependencies. And the dependency graph brings two main benefits. The first one is the parallelization. And on top of that, we actually parallelize each stage of the graph evaluation. The second benefit of a dependency graph, it provides a minimal incremental build. But at the end of the day, it's really the dependencies that are defining the speed of our build. Keep that in mind, guys. So last part, the features. So as we just saw, the graph parsing itself is not a problem in our case. So at the end of the day, we need to build some assets. So actually 99% of the time we spend in our asset build system is building assets, which is quite normal. So all the features here, if we want to make our build even faster, is we need some feature to try to have our build themselves as fast as we can. So the feature I'll be presenting is just for that, so to be alternative to the build function, to try to have those build function as fast as we can. So we're going to go through several of those features. The first one is process isolation, or how to run a build in a separate process. Then build distribution, how to run a build in a separate process on another machine. Caching, how to get build results out of a central network location. File system hooking, which provides sandboxing and third-party executable distribution. And finally, build system as a service, which provides just-in-time compilation and live editing. The first one, process isolation. Process isolation is just a fancy name to say that we want to run a build in another process. By doing so, we have a separate address space. So the build run by itself in its own process. And this has two main benefits. The first one is we can run non-thread safe code because it will be alone in this process. And the second one is we can run one trusted code. So if you need to run some code that some time to time may crash, having it to run in a separate process, whenever you have a crash in this process, you won't crash the entire build, but just the build of this particular asset. Performing process isolation is actually quite simple. All you need to do is start a sub-process in a worker mode and then connect to it through RPCs. So you then send all the relevant information, such as the processor setting, the node data, that kind of stuff. And then the sub-process has all the information required to actually perform the build. And when it's done, you gather the results, which the logs or all the runtime dependencies that might be emitted during the build. And once you have that, actually distribution is quite easy to do as well. The only thing you need to do is actually virtualize your transport layer for your RPC. When you run a build locally, what we're actually using is usually shared memory through a map memory file on Windows. But if you have this layer virtualized, you can actually replace it with some network socket and do this communication through TCP/IP, so it can actually happen on another machine. The only difference, though, is you need to have your remote build interact with the local files. So you need actually to contextualize all the file access to make sure you can replace your file system by network file system, so it can actually interact with the local files. So I already talked about that 3 years ago at GDC. So if you want to know more about our file system stack, I invite you to look at the presentation. So once you have that, you actually all you need to perform the build remotely. The only thing that remains is all the worker management, which is not hard work to do. It's binary transport, thread reservation, knowing which worker has some space available. So all those things is not really hard to do, but it's still some trickier work that needs to be done. It's quite hard to have it right, but it's not that hard. So I'm not going to get into the detail for that. One thing you need to be aware of, though, is that distribution and isolation needs to work together. What I mean by that is, imagine you want to build something locally. So you run your build system. If you have some isolated build, you're going to spawn some sub-process, and your main process and the sub-process are going to talk to each other through shared memory. Now, if you want to do that on a worker machine, as we said before, we need to open a network file system so your worker can actually interact with the file that lies on your local disk. But your worker machine may have several threads. That means you're going to run several builds on the remote machine as well. So you may have several connections back to your main machine. So that's not a problem. But it just shows that if you need to run a build in isolation, it needs to be respected on the worker machine as well. So it's not that hard to do as well. So you need to, in that case, to spawn some sub-processes on your worker machine as well, and those sub-processes can connect back to your main worker. So this is roughly a high-level view of how distribution and isolation needs to work together in this case. Third feature I'd like to talk about is the caching. Caching is just a way of getting the build results out of a central network location instead of doing it locally. What you need to do is actually have a snapshot of all the things that may have an effect on the output. So you need to make a snapshot, find all those information, make a MD5 hash out of that, or any hash, but we're using MD5 in our case. And with this MD5 hash, save the results on a central network location. In our case, we're using what we call the asset store. It's depending on the size of your team, you have to have a backend that is properly sized for the amount of connection that you're going to have. In our case, since we have a lot of people, we need to have a really solid backend. So I already talked about a backend 3 years ago, but it's really something you need to keep in mind, that the backend needs to be properly sized for your team. So then the idea is just try to download the results. You make your key, try to find this key on the server. If you find it, you just have to download the results, and you don't need to build locally. If you don't find it, you can build locally and then publish the results for other users so they can get the results without building the things. One thing to note, it's not always interesting. It's only interesting when your build time is longer than making the key and downloading the results. So it's not actually not interesting for all assets. You need to keep that in mind. Caching needs to be activated per asset types depending on the gain you can have for this asset type. The only hard thing to do in caching is actually building the key. So in our case, we build the key. Our snapshot consists of the asset name itself, the version of the processor, all the settings of the processor, and a hash of all the content of all the source files that have an effect on the output. The output itself contains all the outputs of the build, the file they're going to save on the cache, plus eventually all the runtime dependency that would have been emitted during the build. So fourth feature is the file system hooking. File system hooking is a way to sandbox a process. The idea is to take control over the file system, so you can actually have all the outputs, the file outputs, redirected somewhere else on disk. So you can, doing so, you can actually run several instances of a process that was not meant to run several instances at the same time, because you can actually isolate them thanks to the file system hooking. Another benefit of that is distribution of third-party tools, because you can take control over the file system. You can replace the file system to perform network file operations. You can actually run it on another machine, but have this process actually interact with the file that lies on your local disk. And file system hooking is done through a technique that is called detouring. And here, this is the few slides that I allow myself to geek out a little bit. So it's going to be nice. So imagine you load an executable. When you load an executable, it gets assigned a virtual address space. And this executable can actually load some DLL. Those DLL will be mounted at a certain place into your virtual address space. And in this DLL, you may have some functions with a specific address, such as create file here. So detouring consists of taking the very first few instructions of this function, making a copy somewhere else in memory, and just after this copy, have an instruction, a jump, that jump to the very first next instruction of the one that you have copied. Once you have done that, you can actually invoke the create file function by invoking the code that lies now at address 50. But your entire process is still invoking the code through the address 1 and 20 here. So what we want to do is actually replace what the instruction that we have copied with a jump here. And doing so, all the people that were calling the create file function will now actually be being redirected to your own function, but you can still call the original function by invoking the code that lies at address 50. So it's just another view of what the detouring technique allows us to do. So the replacement function may look like something like that. When you replace the create file function with another create file function, and you can, for instance, replace the path. Instead of opening a given file, you can actually point to another place on disk and just open this other file. And the caller just don't know about it. You're just redirecting to some other place. So the idea then is to have some function that's going to hook all the file system function provided by the OS and replace by your own set of functions. So you're going to write some kind of hook file system function like this one, where you say, okay, replace this system function with mine, with this other system function, these new functions, and give me back the original, a way to call the original function. So the idea here is to write this code, compile it, so now you have a DLL that contains all this code. If you want to hook your own process, something that you can recompile yourself, you just have to link with this DLL. By doing so, you compile with it, you just have to call the hook file system function, and you have taken control over your file system. Now, what if you want to actually do that, but on a process that you cannot recompile yourself? The idea, what you would like to want to do in this case, is actually execute the 3 lines of code, which is load this DLL, call the hook file system function, and that's it. So the idea here is take the 3 lines of code, write the assembly which performs exactly these 3 lines, and then you can actually load your process, but in suspended mode, so nothing executes. Then you can allocate some memory into this remote process, make a copy of your assembly in this remote process, and then execute this code directly into the remote process. Doing so, it will execute your code, you take control of the file system, and that's it. You have control over the file system at this point. You just need to clean things out, and that's it. So geek out terminated, it's done. Stopping. Doing so you can have the 2 things that I mentioned before. You have sandboxing, you can completely sandbox a process, and you can actually send a third-party process on another machine, so you can distribute other process using this technique. So last feature I'd like to talk about is build system as a service. Build system as a service provides 2 main benefits. The first one is JIT compilation. We are a stream game. All our file access are going through a streaming request, and the streaming request is already performing a lot of different steps. One of the first steps is actually reading the data out of the disk, then eventually uncompressing it, then providing this raw data to some C++ class, so we can just build the proper C++ object, and then it can be used by the engine. So the idea here is just to start a build system as a service, as a separate process, and just add 1 step into the already several steps that we have in our streaming request. This step would be connect to the build system, make sure that this asset is built and is up to date, and then go through the other steps. In that case would be read the result out of the disk. You don't need to uncompress anything at this point, so you can skip the uncompressed part, give this data to the C++ class, and provide the result to the engine. So it's really easy way to implement JIT compilation in that case. Another benefit of having a build system as a service is you can perform quite easily also live editing. The idea is to have your build service add a folder watch on your source folder, so whenever a file changes, you get notified. And the build system itself have all the information actually from all the assets using this source file. So we know that we have many destinations using this source file, so we can build a reverse map out of that to know exactly all the destination, all the assets that are affected by this change, and provide this information to the client, to the game. Then the game can take the decision to do whatever it wants, so reload the asset or not. If you reload the asset, can unload it, reload it, and just go through the JIT compilation pipeline and get this asset recompiled on the fly. So you can have live editing this way. So summarizing things up, our pipeline is built what we can call the pipeline trinity, 3 modules. We have the engine as a service, we have the modular specialized tools, and we have the asset build system that is a junction between these two other components. Then we have an asset build system which is built around the dependency graph. Dependency graph provide parallelization and incrementality. But at the end of the day, we need to build some assets, so we have some additional features to speed things up even more for the build itself. So I couldn't end the talk without providing a few numbers. For the nightly build, we're never doing no-op operation. When we launch on our nightly build on our build machine, there is always something to do. So I just performed the no-op operation on my local PC on a rather small graph, which was just 1.5 million nodes. And in that case, it takes 28 seconds to do nothing. And in these 28 seconds, it's actually performing more than 650,000 timestamp check and more than 260 directory listing. Talking about the nightly build themselves, we still need to run our editor to extract some information out of our map. But thanks to the file system hooking, we can actually run many editors at the same time. So we're actually running 20 instances of our editor at the same time, but still running 116 instances of our editor. It ends up in a 20 million node dependency graph that outputs more than 300 whole big files and 18 Far Cry arcade asset packs, all the shaders for the three platforms. So all of this is generating 560 gigabytes of outputs while performing 4.5 terabytes of I/O. And all of this is taking on a single machine, a single beefed up machine for a full build about 2 hours. And an incremental build is about 10 minutes, really depend on the amount of things that have changed. In comparison, on Far Cry 4, we had a third of this work to perform. We had 13 machines, and it was taking 3 hours and 1 hour for incremental build. So I'd like to give some credit to some people that are participated to the stuff I presented today. And special thanks to people that have helped me with the presentation. But if you have one thing to keep in mind, really, is that the dependencies are actually defining the speed of your build. Thank you very much. I think we have still a bit of time for questions if you want.
Hi. So when you talked about engine as a service, you gave the example that the tool exe and the tool exe would instantiate an engine, add a particle system, and that would basically map via an RPC call to the actual engine exe, which would then have like a particle system spawn in the C++ world that it has. So like the engine has thousands of modules in it. How do you actually map all those C++ calls onto like a C# environment of the tool and have everything still match up?
We are using some code generation. We have a system that we call internally Babel. It's just on our code generation tool that generates for us all the RPCs. So we build our API in Babel. It's just a definition file that's actually lists the function that we want. And the tool generates the C# and the C++ code and do all the RPC work by itself.
Okay, thank you.
Welcome.
Did you use fast build and FDB for your persistent build graph, or did you do something, you'd build your own?
Oh no, it's our own code.
Cool.
What I said at the end, I've worked with Franta when
Right.
fast build on Far Cry 4, but so got some inspiration
Right.
out of the way fast build work. Mm-hmm. But what we have here is like a supersede of what fast build does. We could do some code compilation with our system. It's just dependency graph. So
right.
You can extract your dependencies, and we could do some code compilation with that.
Mm-hmm.
Hi. So, cool presentation. One question, since the dependency graph defines your build speed,
Yeah.
did you develop also some tools to analyze those huge graphs and figure out what the problematic links are in there so you can help content creators change dependencies or maybe move stuff around?
So we didn't develop some tools, but we are following every day. We have some statistics out of our builds. So whenever something happens and the build time are actually exploding, we can actually have a look at what has been rebuilt, why. And we have some logs. Actually, we can see that a certain type of asset, for instance, for a given build, has completely exploded compared to the previous build. The main reason for that could be a processor version change, for instance. In that case, it's normal. We need to rebuild all those assets at least once. And some other times it was because some crazy dependency was inserted, and then you can just take one of those assets and actually build this asset and debug it and understand what for this asset has changed. We can also have all the logs to know what has been the reason for why an asset has been rebuilt. So, but you can just do one in isolation to understand what happens and see what is the change that's actually causing more dependency to be inserted.
Okay, thanks.
A few quick questions. You said you use MD5 for your hashing for like caching.
Yes.
Did you ever consider other hashes?
No.
Alrighty.
But we didn't have any issue with MD5. It's here. It works.
Yeah. So when you're using the engine as a service for the editor, for tool.exe or whatever that is, that includes calling out to the engine to do rendering you need to do?
When we start, actually, the engine as a service, we can ask him to start with a viewport or not. We can create a viewport on demand. And then we can actually map this viewport to whatever window we want. So usually our tools are providing, okay, here is a viewport, is a window handle, and you can actually have the viewport into your tool.
Okay. And with distributing asset builds across multiple machines, because with one machine with just a lot of cores versus just multiple distinct machines, something that has prevented us from considering stuff like that is the overhead of copying files to different machines.
We're not copying anything on different machine. That's the thing. We have the worker directly interact with the file on the builder, the one that is performing the build. So the worker just get the IP address. We open the file system server on the local machine. The worker just connecting back to the main machine and interact with the files that lies on the machine performing the build. So we have nothing to. The only thing we need to distribute is actually the executable. So whenever some executable has changed, we need to actually send this new code to the worker and restart the worker process.
So when I'm working locally and I change something and then I PPD it or whatever, then it's my machine is the one doing the work and I'm not like farming out to other people.
Yeah, it's doing that. Actually depends. It's a command line options when you say I want to be in distributed mode. So in that case, we're going to look at we have a folder actually where all the workers are registering. So we find a token in this folder saying, okay, this machine is available. Try to connect to it. But if you launch in distributed mode, then it's actually a task, and this task can be grabbed by the local workers, threads in our process, or by a remote worker which has another thread which connect to the worker and try to grab some task out of the pool of tasks. So usually, if you don't have that much to do, it will always build locally instead of being grabbed by a remote process. But when you start to have a lot of those, it actually distributes nicely.
Well, but when you have a lot of work, it's probably because you've edited a lot of stuff, and to distribute that, you have to copy all of your edited files out to the workers.
But we're not copying files out of the workers. The workers directly interact with the files that lies on your local disk. So you just grab a task. The task is build this asset, and by building this asset, we'll read the source file
On your local machine.
on your
over
local
the
machine,
network.
perform the build, and write the output on your local file, on your local PC.
Thank you.
Welcome.
Thank you. How did you guys handle any? Was there any variant processors, I think you called them, or do you guys, are they all invariant? Like if there's multiple choices, essentially, do you have any sort of query language for
No,
A or B?
we are using, as I said before, everything is a node. So we have some virtual node that are actually selectors.
Oh, so the selector node then.
So it's a node associated to a processor that is a selector, and we'll look at the different alternatives to pick the right one.
So there was parameterized kind of processes at some time, but that was done through passing it through that node.
No, usually, for instance, let's say we want to build a geometry. So you have the geometry, the final geometry will depend on the geometry source selector, which is associated to a different node, associated to a different processor. So building this node is actually, this virtual node doesn't have a build, it just have an extra dependency extraction function. This one will look at what we have on disk and take the proper file, as that as a dependency. And the geometry itself will say, okay, give me your inputs. Actually, this giving the inputs will parse the graph to get all the proper file that actually reference as a dependency, and then work with those files.
Cool, thank you.
Welcome.
Hi. Do you have post-serialization runtime code to avoid rebuilding the full assets?
Excuse me, I didn't get that.
Do you have post-serialization in your build system?
Serialization?
Yeah. So, for example, when you're adding some new settings for existing assets and you don't want to rebuild it for all machines, but just to try it.
But what you can do is, for settings, as I said before, whenever the definition file change, we know that we need to rebuild the asset, the binary version of those settings. But it always goes reverse side. That means at some point the NG will ask, give me those settings. Those settings build system will look, okay, is it up to date or not? And we'll go through all the dependency to see if it's actually up to date, build if it needs to be built, and then loaded by the engine.
Yeah, but you mentioned versioning. So
yeah.
Do you support different versions of your assets? So when you change the version, you have to rebuild?
No, when you change the version, everything associated to the processor that has to change its version will be rebuilt.
Okay, thank you.
For the asset data object model that you have, if you ever need to add a parameter to an asset type, for instance, you need to add a parameter to a particle, and previous versions of that particle or other particle assets do not have that parameter in them, how do you adapt those previously built assets to then conform to the new data model?
The two possibilities, if you change the version number of your processor, all those assets need to be rebuilt from scratch. So it will be rebuilt with the new settings. Or you can, in your own processor, say, okay, I want to support the older version of those assets and write your own code that will take care, okay, what is the minor version of this asset, and write the code to support older or new version. But usually we just bump the version number of this particular asset, and then they will be all rebuilt. Usually it's happened on the build machine whenever you submit your change. The build machine will take this code, go through our automated test farm. So most of those assets will be rebuilt and pushed on the cache. So for all the user, whenever the build is actually released, all those assets are already built and on the cache.
Thank you.
For the difference in time for Far Cry 4 build time versus Far Cry 5, what were the things that you were identifying when starting Far Cry 5 that you eventually saw were the biggest benefits in improving the build time?
But at the end of Far Cry 4, it was still a long process having our build out. And we knew that Far Cry 5 will be a lot larger game. So that's why we started to say, okay, we need to improve our build pipeline, asset build pipeline. So we started to work on that, but I've been actually completely amazed by the final numbers that we had and the number of assets and the millions of dependency. I was not expecting that. But we gladly saw that it worked fine, and we're able to ship our game.
Okay. Were there clear bottlenecks in the old pipeline that you were targeting specifically?
But all the graph, it was not a graph per se. It was still trying to manage the dependencies. So we're going through in this way, but it was not a perfect graph. And all the processing, like the no-up build was several minutes or several tenths of minutes, for instance, while now it's 1.5 million node in less than 20 seconds. You know, we're not talking about the same numbers at all.
Okay. Thank you.
Welcome.
With your engine as service, are you able to auditor the game from a remote machine? For example, update some assets position in editor and preview in real time on console.
It could be done, but we are not using it right now. Thanks to our RPC system, it can be cross machine. We're using with shared memory right now on the same machine, but it could be cross machine. We're not using it right now, but yes, clearly this is something we're going to leverage later. Oh, it's done? Okay, well, sorry. Thank you very much, guys.